You're a person. You've got genes from your parents and a childhood that may or may not have involved emotional support. Somewhere between those two forces, you became this. Congratulations. Developmental psychology is the study of how that happened, from birth to death. Nature versus nurture. So here's the original fight. Researchers have been studying twins for decades, and the data keeps landing in the same range. About 50 to 70% of the variation in IQ comes down to genetics. One massive meta-analysis looked at over 14.5 million twin pairs and found overall heritability sitting at about 49% across traits. That's not a small sample. But here's the problem. When scientists go looking for the specific genes responsible, the common variants they find predict only about 2 to 5% of IQ variance. So how can something be 70% heritable and yet genetically unpredictable? That gap is called the missing heritability problem. And it's not a rounding error. The critical thing to understand, heritability does not mean inevitability. Both genes and environment matter, and the question of how much and when is still very much unresolved. Every theory we're about to cover is basically an attempt to answer that from a different angle. Let's start with the guy who thought kids basically rebuild reality inside their heads, one stage at a time. Piaget's cognitive stages. So how does a kid actually learn to think? Jean Piaget said it happens in 4 stages: sensoromotor, pre-operational, concrete operational, and formal operational. And these aren't just getting smarter over time. Each stage is a fundamentally different way of processing reality. A toddler isn't a dumber adult. They're running completely different cognitive software. The first stage, sensoromotor, covers birth to about 18 months, and Piaget broke even that into 6 sub-stages. 6 for babies. The man was thorough. Now here's a fun detail most textbooks skip. Piaget's famous 4-stage model wasn't his first attempt. Before 1936, he had a totally different 3-stage framework involving autism, egocentrism, and deductive thinking. He scrapped it, rebuilt from scratch. Even Piaget didn't believe his first theory, which is honestly what good science looks like. But here's the problem. The stages sound clean, and reality isn't. Kids don't flip a switch at age 7 and suddenly think logically. A child might show concrete operational thinking in one domain, like understanding that flattening a ball of clay doesn't change how much clay there is, while still being completely pre-operational in another. The map is useful. The territory is messier. So if Piaget gave us a model of how thinking develops, what about the rest of the person? Emotions, identity, trust, Vygotsky's socio-cultural theory. So Piaget thinks kids figure stuff out on their own, like tiny solo scientists. Vygotsky says, nah, you learn to think by doing it with someone else first. Every higher cognitive function, problem solving, reasoning, planning, starts as a social activity between people and only later moves inside your head. Thinking is a team sport before it's a solo one, and the operational core of this idea is something called the zone of proximal development, or ZPD. It's the gap between what you can do by yourself and what you can do with help from someone who knows more than you. A parent, a teacher, a slightly smarter friend. The ZPD isn't a metaphor. It's meant to be a targeting system for instruction. You aim your teaching right inside that zone, not at stuff the kid already knows, not at stuff that's way over their head. Here's what's wild. Vygotsky developed all of this in roughly a decade, working under Soviet censorship, and died in 1934 at age 37. His entire theoretical program compressed into basically one career sprint. Western psychologists didn't even get proper access to the ZPD framework until decades later. But here's the problem. How do you actually measure with assistance in a standardized, replicable way? Scaffolding, peer tutoring, formative assessment, all of these trace directly back to the ZPD, enormously influential in education. But operationalizing it rigorously, still genuinely contested. So we've got 2 ways to think about how kids develop cognitively: solo exploration versus social guidance. But what about the stuff that isn't purely cognitive? What about identity, trust, and all the emotional chaos of growing up? Erikson's psychosocial stages. So Piaget gave us a map of how kids think. Erikson said, cool, but what about the rest of your life? His framework covers 8 stages from birth to death, and each one is built around a central conflict. As an infant, it's trust versus mistrust. As a teenager, it's identity versus role confusion. As an old person staring at the ceiling at 3 a.m., it's integrity versus despair. The big innovation here is that development doesn't stop when you turn 18. Every decade of your life has psychological stakes. And this isn't just vibes. A longitudinal study followed 159 men across 2 cohorts, one from Harvard, one from inner city Boston, from their 20s all the way into their 80s. The men who successfully navigated Erikson's midlife psychosocial task showed better emotional well-being learning and sharper cognitive health at ages 75 to 85. And here's the kicker. That held up even after controlling for adolescent intelligence and education level. So it's not just smart people age better. It's that how you handle the psychological conflicts of your 40s and 50s has measurable downstream effects on how your brain works 30 years later. But here's the problem. Erikson's 8 conflicts were shaped by a specific time and culture. Identity versus role confusion hits differently in a hyper-individualistic Western society than in a collectivist one, where your identity is largely defined by family and community. The framework needs adaptation, not just application. Still useful, still limited, like a map drawn before half the roads existed. So Erikson zoomed out across the lifespan. But what if development isn't really about what happens inside your head at all? Kay Wahlberg's moral development. So we've got cognitive stages, psychosocial stages, and social scaffolding, but none of those really answer a pretty basic question. How do you learn right from wrong? Lawrence Kohlberg had a theory. He proposed that moral reasoning develops in 3 levels, each with 2 stages, giving 6 stages total. Level 1 is pre-conventional. This is where kids start. You don't steal the cookie because you'll get punished. Or you do steal the cookie because you want it and nobody's looking. It's pure self-interest. Level 2 is conventional. Now you follow rules because that's what good people do. You care about social approval, law, order, fitting in. Most adults live here permanently. Congratulations. Level 3 is post-conventional. This is where you reason from abstract ethical principles that might actually override the law. Think civil disobedience. Think the rule is wrong, so I'm breaking it on principle. Most people never consistently reach this level, but here's what made Kohlberg genuinely interesting. His method wasn't a quiz with right answers. He gave people moral dilemmas. The most famous one, a man named Heinz has a dying wife. The only drug that could save her costs way more than he can pay. The pharmacist won't lower the price. Should Heinz steal it? Kohlberg didn't care whether you said yes or no. He cared about why. The reasoning was the variable, not the verdict. 2 people could both say yes, steal it, and land at completely different stages depending on their justification. But the model had a problem. Carol Gilligan argued that Kohlberg built his entire scoring system around justice and individual rights derived mostly from studying men. Women in his framework often scored lower, not because they were less morally developed, but because they emphasized care, relationships, and responsibility to others, and the scoring system treated that as less sophisticated. Gilligan didn't just add a footnote. She challenged what morally advanced even means, so moral reasoning develops in stages. But what about the emotional bonds that shape us before we can reason at all? Bowlby's attachment theory. So why do babies get attached to their caregivers? For a long time, the dominant answer was simple. Food. Mom feeds you, you learn to love mom. Classic behaviorist logic. Pair a stimulus with a reward enough times, and boom, you get a bond. John Bowlby thought that was nonsense. His argument was that attachment isn't learned through feeding at all. It's biological. It's baked into us by evolution. Babies don't cling to their caregivers because caregivers hand out snacks. They cling because for millions of years, the babies who stayed close to a protective adult were the ones who didn't get eaten. Attachment is a survival system, not a conditioned response. And Bowlby didn't just theorize in a vacuum. Here's where the story gets good. In August 1957, Bowlby sent a draft of his paper, The Nature of the Child's Tie to the Mother, to a guy named Harry Harlow, an experimentalist running a primate lab in Wisconsin. By June 1958, Bowlby had visited Harlow's lab in person. One was building the theory in London, the other was building the experiments in Madison. And they were literally exchanging drafts and lab visits, each one strengthening the other's case. By 1969, Bowlby was explicitly crediting Harlow's work as empirical proof for what he'd been arguing theoretically. Bowlby described 4 core features of the attachment system. Proximity maintenance, meaning the infant stays close to the caregiver. Safe haven, meaning they return to the caregiver when threatened. Secure base, meaning they use the caregiver as a launchpad for exploring the world. And separation distress, meaning they protest when the caregiver leaves. These aren't poetic descriptions. They're specific behavioral markers that later researchers used to actually measure attachment in the lab. So Bowlby gave us the theory. But what about the experiment that proved caregivers aren't just vending machines? Bronfenbrenner's ecological systems. So far, every theory we've covered has been zoomed in. What's happening inside the child's head? What's happening between the child and their caregiver? What stage is the child in? Bronfenbrenner said, that's not enough. You cannot understand a child's development by studying the child alone. You have to map every layer of environment wrapped around them. He organized these layers into nested systems, kind of like Russian nesting dolls, but less cute and way more consequential. Innermost layer is the microsystem, the stuff directly touching the child's life. Family, school, peers, the neighborhood. Then you've got the mesosystem, which is how those direct settings interact with each other. Your parents' relationship with your teacher, that's mesosystem. It affects you even though you're not part of that conversation. Now here's where it gets interesting. learning, the exosystem is made up of structures the child never directly participates in, but that shape their life anyway. Your parents' workplace, for example. The child has never set foot in that office, but if mom gets laid off on a Tuesday, that kid's world changes by Wednesday. Then there's the macro system, the big stuff: culture, economic systems, political ideologies, laws, and finally, the chronosystem, which is just time. How all of these layers shift and change across the child's lifespan. The practical takeaway is powerful. Two kids sitting next to each other in the same classroom can be having completely different developmental experiences because their exosystems and macro systems are radically different. One parent has job security, the other doesn't. What looks like an individual difference in behavior might actually be a system-level effect wearing the costume of a personal trait. Bronfenbrenner later revised this into the bioecological model, adding what's called the process-person-context-time framework, basically acknowledging that the child isn't just passively soaking up environmental layers. The child's own characteristics actively shape how those environments respond to them. It's a two-way street, so we've zoomed all the way out to culture and economics. Now let's zoom back in to something much smaller and much more disturbing: language. Acquisition device. Here's something weird. Children learn language absurdly fast. By age 3 or 4, most kids are producing grammatically complex sentences, asking questions, embedding clauses inside other clauses. And they do this despite the fact that the language they hear around them is kind of a mess. Adults speak in fragments, interrupt themselves, make errors, trail off mid-sentence. The input is noisy and incomplete. So how do kids extract perfect grammar from imperfect data? Noam Chomsky argued they don't. Not from data alone, anyway. He proposed that children are born with a built-in mental mechanism specifically designed for learning language. That's the language acquisition device, or LAD. The idea is that something in the architecture of the human brain already knows the deep rules that all languages share, a kind of universal blueprint. Chomsky called this universal grammar, and in a 2002 paper, he narrowed the uniquely human piece down to one operation: recursion, the ability to embed structures inside structures infinitely. The dog that chased the cat that ate the fish that swam in the pond. You can keep going forever. That's recursion, but here's where it gets messy. There's a ticking clock. Penfield Roberts and later Lenneberg proposed that language acquisition has a critical period, a biological window that closes. The evidence? Case studies like Jeannie and Chelsea, children deprived of language input during childhood who never fully acquired normal grammar even after years of instruction. Johnson and Newport's 1989 study of Korean and Chinese immigrants showed steep drops in grammatical ability for those arriving in the US after about age 7. So is the LAD real? It depends. Recent empirical work supports a competing view, that kids are just incredibly good statistical learners, extracting patterns from input using general-purpose brain machinery, no dedicated language module required. Chomsky's own claims have narrowed considerably over the decades. The field is genuinely split on this, and honestly, that's kind of the point. The debate isn't a failure, it's science doing its job, so language has a window. But does the brain ever truly stop changing? Bandura's social learning. In 1961, Albert Bandura brought 72 children into a lab at Stanford and showed them something simple: an adult walking into a room with an inflatable Bobo doll. In one group, the adult beat the absolute hell out of it, punching it, hitting it with a mallet, yelling specific phrases at it like "sock him in the nose." In another group, the adult played calmly with some toys. A third group saw no model at all. Then the children got their turn in the room. The kids who watched the aggressive adult didn't just get a little rougher. They reproduced the exact behavior. The same punches, the same mallet strikes, the same phrases. Nearly 90% of children in the aggressive group imitated what they saw. And when researchers checked back 8 months later, about 40% still retained aspects of that modeled aggression. 3-year-olds memorizing violence like it was a nursery rhyme. But here's the part that broke psychology wide open. None of these kids were rewarded for being aggressive. Nobody gave them candy for punching the doll. They just watched someone else do it and saw that nothing bad happened. That was enough. Bandura called this vicarious reinforcement, and it shattered a core assumption of behaviorism. You don't need direct reinforcement to learn a behavior, you just need to see it modeled. That's observational learning. And it was a big deal. Bandura later expanded this into something called social cognitive theory, which added 2 major ideas. First, self-efficacy, which is your belief in your own ability to actually do something, and second, reciprocal determinism, the idea that your behavior, your personal factors, and your environment all shape each other simultaneously. You're not just a product of your surroundings, you're also producing them. So kids learn by watching. But what about the thing they learn fastest and most naturally of all? The strange situation. So Bowlby gave us the theory, but theories without measurement are just vibes. In 1970, Mary Ainsworth decided to actually test this stuff. She designed a lab procedure called the strange situation, and it's beautifully simple. You take a caregiver, an infant, and a stranger. You put them in a room. Then you run 8 short episodes, about 3 minutes each, where the caregiver leaves, the stranger enters, the caregiver comes back, the stranger leaves, and so on. Basically, you're creating a controlled stress test for a baby. Not cruel stress, just where did mom go stress. What Ainsworth was watching wasn't the separation, it was the reunion. How does the infant behave when the caregiver comes back? That's where attachment shows itself. Her original Baltimore sample of about 100 middle-class American infants produced 3 clean categories. Roughly 65% were secure, meaning they got upset when mom left but calmed down quickly when she returned and used her as a home base. About 22% were insecure avoidant, basically ignoring the caregiver's return. And about 13% were insecure resistant or ambivalent, clinging but not actually being comforted. Later, Main and Solomon added a 4th category, disorganized, for infants showing contradictory or collapsed behaviors, roughly 5 to 10% in US samples. Now here's the interesting part. Cross-cultural research found that the 65% secure baseline holds pretty consistently worldwide as a global mean, but the insecure subtypes shift dramatically by culture. German samples show higher avoidant rates, which makes sense because German caregiving traditionally emphasizes early independence. Japanese and Israeli samples show higher resistant rates consistent with high proximity caregiving norms. Same procedure, same species, different cultural logic underneath the numbers. The strange situation turned Bowlby's evolutionary framework into something you could actually measure and replicate. Its influence on pediatrics, policy, and developmental science is enormous. But it's worth noting the real critique. A lab stress test with a stranger is not the same as real-world attachment. That's a genuine limitation. Still incredibly useful, still not the whole picture. So now we have a way to classify how infants attach. But what happens when those infants grow up and start watching other people? Harlow's monkeys. In the late 1950s, a psychologist named Harry Harlow set up an experiment that sounds almost too simple. Take infant rhesus monkeys, separate them from their mothers, and give them 2 options: a wire surrogate mother that dispenses milk, and a soft cloth surrogate that gives absolutely nothing except the feeling of something warm and soft to hold onto. Now, according to drive reduction theory, which was the dominant view at the time, the answer was obvious. Infants bond with caregivers because caregivers provide food. Hunger drives attachment. So the babies should prefer the wire mother. She's got the milk, she's got the goods. They did not prefer the wire mother. The infants overwhelmingly clung to the cloth surrogate. They spent most of their day pressed against it. When something scared them, they ran to the cloth mother, not the one with food. They'd occasionally reach over to the wire mother to feed, then immediately scramble back to the soft one. The tactile experience of warm, soft physical contact was itself a primary need, not some byproduct of getting fed. That finding had a name: contact comfort, and it was direct experimental support for what Bowlby had been arguing on the theoretical grounds. But Harlow didn't stop there. He also ran social isolation experiments. Some lasted months, some lasted a full year. He built a stainless steel isolation chamber he called the Pit of Despair, designed to induce total helplessness. Monkeys isolated for extended periods came out profoundly broken. They couldn't interact with peers. They attacked themselves. They couldn't mate normally. Some showed near total behavioral shutdown. The ethical fallout from those experiments has never gone away. Harlow's isolation procedures are widely considered among the most disturbing in the history of comparative psychology, and the standard defense, it was a different era, doesn't entirely hold. Contemporaries raised objections at the time. The findings were real and consequential. So was the suffering they required. So what did all this attachment research actually look like when someone tried to measure it in human infants? Neuroplasticity in aging. For most of the 20th century, the assumption was simple: your brain peaks in your 20s, then slowly declines. Turns out that's wrong. Randomized controlled trials using MRI scans show that older adults who exercise regularly have greater prefrontal gray matter volume than sedentary peers. That's measurable structural change. In one experiment, older adults who learned to juggle for 90 days showed gray matter increases that correlated with their skill level at 65, at 70. The brain was literally reshaping itself in response to new experience, and it's not just physical exercise. Longitudinal data links social isolation to approximately 60% higher dementia risk in older samples. Social connection isn't just nice to have, it's a neurological protective factor. But here's the honest caveat: some structural gains faded after people stopped training. Whether improvements transfer to real-world cognitive functioning is inconsistent consistent across studies. We can't prescribe a specific brain workout with guaranteed results, but the old default that aging brains are fixed and only declining is empirically dead. Plasticity persists, and that brings us full circle. This video opened with the oldest debate in developmental psychology: nature versus nurture. Neuroplasticity in aging is the answer at the end of the lifespan. Your brain is still being shaped by what you do at 75. The debate doesn't have a clean finish line. It just keeps going all the way to the end. If you enjoyed this video and want to see more, click the video on the screen now.